Welcome. In this video I'll start linearizing ideal MHD and show how you can use this to study waves and instabilities in plasmas. So we've so far looked at equilibrium solutions where you have a steady state, nothing is changing in time. Now we're going to see what happens when you add a small perturbation, so you give the system a small kick. Does it ring like a bell, or does it go unstable and result in essentially destroying the equilibrium? So to look at this, we'll look at small fluctuations, so small changes around an equilibrium, so we can linearize these equations. I'll show you what that means and how we do that. And then we'll start to look at what the properties of these solutions look like, so the waves and the instabilities. So we're going to start with ideal MHD. And if you haven't seen the derivations, this is lecture 5, so B and D. And so we have equations for the density. So we have a mass density rho, and it looks a bit like this. So we have a U. So this is the advection with a velocity U. And then here we have a compression, so divergence of U. Then we have an equation for the momentum itself. So we have a momentum. So it's the mass density times velocity. And then here we end up with, again, advection. In here, and here we should have brackets around this so that the rho is multiplying both these terms. And then on the right hand side we have the forces, so this is the pressure, gradient P, and then we have the electromagnetic force, so J cross B here. And then we have the pressure equation, which looks very similar to the density equation. So we have the pressure here, and this just comes from the adiabatic gas laws. So we have U dot grad P, and then here we're assuming that this is adiabatic, so we have a ratio of specific heats gamma, P divergence of U. And then finally we need an equation for the magnetic field, and we use Ampere's law, and we write that dB by dt, and this ends up being curl of U cross B. So it's curl of E is minus dB by dt, and then E plus U cross B is equal to 0. It's ideal MHD Ohm's law. And so we have an equation for the magnetic field, and then an auxiliary equation for J, the current density, and this is just 1 over mu naught curl of B. Okay, so we have these equations, and this makes a closed set of equations for the density, the velocity, the pressure, magnetic field, and an equation for the current. And so far we've looked at stationary solutions where d by dt was 0, and this meant that the only terms that were important were these two here. So for equilibrium solution, J cos P is equal to grad P, at least if the velocity is 0. But now we look at what happens when you make small changes to these quantities. And what we're going to do is we're going to write all quantities, for example, rho. Rho is some function of space and time, but we can split it into two pieces. It's an equilibrium part, and the d by dt of this is 0, so d rho 0 by dt is equal to 0. This is the equilibrium part, equilibrium. And then we're going to make a small change to it, and then this is going to have also a d rho, which might depend on space and time as well. And so this is time varying. Well, this is the equilibrium part. I'm going to assume that delta rho is much smaller than rho naught, and this will mean that we can neglect things like delta rho squared or multiples of perturbed quantities. And so we essentially substitute this into each of these equations, and the same for the other quantities. So U becomes U naught plus delta U, P becomes P naught plus delta P. And I'll show you how this is done for one equation, so for the density. So we have a d by dt of rho naught plus delta rho, and of course the d by dt of the rho naught goes to 0. And then we have various other terms. So we have, for example, a u naught dot grad rho naught, and then on the right hand side we have a minus rho naught grad divergence of u naught. And so these terms involve only equilibrium quantities. These are all equilibrium. And then we have terms which involve only one perturbed quantity. So we have we can perturb, say, this part first. So we have delta u dot grad rho naught plus also a u naught dot grad delta rho. And on this side again we might have minus delta rho divergence of u naught minus a rho naught divergence of delta u. And so these quantities all involve just one perturbed quantity, and these are the linear terms. And then we have the non-linear parts, which are, so we have the delta u naught dot grad delta rho naught, and then on the right hand side we have a delta rho naught and then divergence of delta u naught. And so if we compare the size of these quantities, so the equilibrium components, they must cancel, because by definition these are in balance when you solve the equilibrium problem. So these all cancel out. These we assume here, these are nonlinear terms, both this part here and this part, and these we assume are small compared to the linear parts. And so the only parts we keep are essentially this part in the middle. So we have a d by dt of delta rho, and we're going to keep all this stuff, which is all proportional to a single value, a single perturbed quantity. And so this part together with that time derivative is going to be the equations we solve. And so we end up with an equation for the density perturbation. So we have d by dt of delta rho. And then we can write down the same things for the other equations. So we do the similar expansion. So all quantities expand as an equilibrium part and a perturbed part. And I'll just write them out here, and then we can go through them. So I've written out the equations for the momentum equation, the pressure equation, and the magnetic field, the induction equation. And you see you just end up with lots of terms, but they all have one equilibrium quantity, one or two, and then importantly only a single perturbed quantity. So each of these terms just have a single perturbed quantity. So here it's delta p rather than here it's delta u, here delta b, and here single delta b. And so the size of each of these terms is proportional to the size of the perturbation. And this will allow us to write this all in essentially a giant matrix equation. And so we can apply linear algebra methods to solve it. And you see it's messy, but it's relatively straightforward after a bit of algebra. Okay, so all these terms we can then write as a set of coupled equations. So there are various ways of doing it. One way of doing it is to write all this as just one big matrix operator. So we have a state which consists of a mass density perturbation, a velocity perturbation, pressure perturbation, and a magnetic field perturbation. And the time derivative of all of these is a big operator, which all consists of things like curls, multiplications, and these can all be written as a big matrix, which I won't write out here because it basically consists of all these terms here, operating on delta rho naught, delta u, and delta b. So for example, if you wrote these equations out in a finite difference method or finite element, each of these operators would become essentially elements in a matrix. So just multiplying by taking differences between grid cells, for example. And so this would fill in essentially elements of a big matrix, and then you can solve it that way. But it turns out that's a slightly wasteful way of doing it, at least for linear MHD, because here we have many variables. So we have 8 quantities, so 3 components of velocity, 3 components of magnetic field at each point, and we can actually simplify this quite a lot if we think about it for a little bit. So the first thing is that because this is an equation where the time derivative of the left-hand side is proportional to itself, so we have an equation where we have like a df by dt is some constant times f. It's a linear operator, and so therefore the time derivative here is just, so here would be f is proportional to e to the I omega t, where omega was a frequency. So if omega is real, then it's oscillation, so you have an oscillating solution. If omega is imaginary, then you have an instability. If omega, so typically you're right that gamma is I omega, and then this corresponds to growing or shrinking solutions. Growing or shrinking. So it's either growing unstable or decaying away. Okay, but we can write this equation essentially by substituting all the terms into one of the equations. And usually the way this is done is to substitute everything into the momentum equation. So we take this equation for velocity u, and then substitute essentially this, here we have a delta p. We're going to take this delta p equation and substitute it into here. Take that one there, and then we're going to take the delta b and substitute into here and there. And this is relatively straightforward, but it means you need to differentiate this in time. And so we take derivative d by dt of this whole equation, then you have a d delta p by dt, substitute in this expression, and here you have d delta b by dt, and you substitute in this expression. And you end up with one equation for delta u, which only depends on delta u, and that you can then solve to find the frequencies or growth rates of instabilities. As you can see, though, this will get quite messy. So for now, we'll set u naught equals 0, and that simplifies this quite a lot. So that you can follow through and do the calculation with u naught in there, but just the number of terms becomes very large. So I'll show how this works down here. So if you take the second derivative of the velocity equation while setting u naught equals 0. So this is substituting in here the delta p equation here, becomes the d by dt here, becomes this part here, and then the delta b by dt here, substitute in this bit, and this again substitute in and becomes that, and now we have an equation which has, on the left hand side you have a second derivative of u with time, which, because it has this frequency dependence, this we can just write as a minus omega squared delta u. So I've actually just written by just using this expression, which recognizing it's of this form, and then bring out two I omega factors which come in minus omega squared, and we have an equation on the right hand side which is a bit complicated, but it's all proportional to delta u. And we can start to recognize some of the terms in this equation. So for example, you can pull out this gamma p naught divided by rho naught, and these two together, so gamma p over rho is a sound speed. So it's a sound speed squared. And for example, these terms here, so here we have, so get a different color. So here we have a b naught here and a b naught. So we have b naught squared, and here we have a mu naught rho. So b naught squared over mu naught rho naught. This is the alphane speed. This is v alphane squared. So these two terms here, this is similar, you have a b naught squared here. These terms will give us alphane waves, this one will give us sound waves, and we'll see in next lecture how this is done and how this works in general.